Howdy. We're going to look at a topic today called spontaneity or thermodynamic favorability. What this kind of means is whether something is going to happen naturally or in real life. If it's favorable, it wants to happen. If it's not favorable, it does not want to happen. In the past term we used to use for this is spontaneity, whether something was spontaneous. But I think thermodynamic favorability is a better term for this. So let's just take a look at some processes that we've already looked at. Let's say this is methane, and methane is burning, okay? So if I want to burn methane, what does that look like? Well, this process, I light it, we emit heat, and the delta H is negative. So if I start here on the graph and I put in some spark, where's it going to end up? Well, it ends up lower than what we started at. And so this emits a lot of heat, and it wants to happen. Once you get going, it's going to keep going and wants to burn. If I try to do this backwards, if I start at CO2 and H2O, can I change it back to methane? Easily? No. It takes a lot of energy. I have to go all the way up this hill if I want to go backwards, like this way, right? So that does not want to happen. So that is not a favorable process if I want to try that, make that happen. So if I burn something, releases energy, that's favorable. Let's look at this one here. I have H plus, which is an acid. OH minus, it's a base. I mix them together, they form water. Well, water forms also exothermic. So that's going to also look like this. If I take water and I want to try to change it back to H plus and OH minus, is that going to happen easily? No, that's not going to happen very easily. Okay, so exothermic things want to happen. They are very favorable. What about this? If I have an ice cube and it's melting, well, is energy going in or is energy coming out of the ice cube? In this case, to melt it, energy goes into the ice cube. And so this ends up being an endothermic process. But we know this happens. So endothermic things can also happen because it doesn't have to be exothermic in order for it to happen. We know an ice cube melts if I just let it sit there. And so why is this? And the reason for this has to do with not just enthalpy, but also something called entropy. So we're going to talk about entropy today and how that determines spontaneity. Let me once again, spontaneous means thermodynamically favorable. So this is the main thing you need to know is this right here. If it's spontaneous, it is favorable. If it's not spontaneous, it does not mean it's favorable. It does not mean instantaneous. It doesn't mean it happens right away. An ice cube melts. It does not happen immediately. It takes a long time for an ice cube to melt sometimes, depending on the temperature. It could take many, many, many hours. So, and how big the ice cube is and all that stuff. So spontaneous does not mean instantaneous. It just means it's favorable. All right. So entropy, this is the term that we're going to start looking at today. Entropy is the other factor besides enthalpy that determines favorability of something. What does entropy mean? Well, it's how dispersed the energy is. So if I have something that is very dispersed, that's got high entropy. If it's not dispersed at all, if it's all compact, it's lower entropy. So traditionally, it was talked about the disorder of a system. Dispersal is a better term now. And the greater the entropy, the more it's dispersed. So if I get the particles dispersed, if I have energy dispersed, that is, if I have energy in particles and it spreads out, that is increasing entropy. And finally, the second law of thermodynamics says that entropy of the universe will always increase. The universe is expanding. Everything wants to get more dispersed. There's no way that my room stays clean. It takes a lot of energy to put it back together, but over time, it just gets messier and messier. You know me. That's how my room is, but my desktop is. So that's entropy at work. Okay. So these are the scenarios. You can jot these down. If I melt a solid, like we saw, it's going to increase entropy. If I dissolve things, so if I take something and I put it a solid into liquid and it spreads out, also increasing. If I change phases and I go from solid to liquid or liquid to gas, increasing entropy. If I have a reaction, this is reaction here, and I produce more products than I have reactants, I start with fewer things and I end up with more, also increasing entropy. And then finally, when T increases, generally speaking, increasing entropy. Okay, so let's look at a couple of scenarios. Let's look at this. Is this going to happen? So if I have gas here and I open this valve, what's going to happen? Well, the gas is going to spread out. And it spreads out into two different things here. And that is favorable. Is it favorable for the gas to start spread out and end up back in one container? No, it doesn't want to happen. So that's not favorable. And that's what we're trying to think about when we're determining spontaneity of stuff. So scenario one, solid melts. Entropy increase or decrease? And we spread out, so entropy is increasing. What about liquid freezing? Well, I have a liquid, it's moving around more, and then it forms a solid, which is less, so my entropy decreases here. What about boiling a liquid? I go from liquid to gas, increase it, so positive entropy. What about sublimation? Solid to gas, increasing it. And then finally, dissolving a substance, spreading out, also increasing. Let's look at some equations. So what if I have this right here? I have a solid, KClO4 goes to KClO3 and O2. Well, I'm forming a gas right here. And so this is going to make it spread out. So I have positive entropy here. What about this scenario? Well, this is condensation, gas to liquid. I go from a gas, condense down, so this is a negative. What about this one right here? Solid, liquid, goes to aqueous and gas, and spread out, positive entropy. Well, I have 1 mole here, 2 moles here, spreading out, increase it. What about this one here? Well, this one I have 2 moles on the left and 2 moles on the right. I can't figure that out. So based on entropy alone, I can't determine it. I'd have to look at some numbers, I have to do some calculations, and I can look at the enthalpy and figure out how is it related. So when you have something that you cannot figure out, you can look at both terms and remember I have delta H right here. So delta H, when it's positive or negative, which one's more favorable? And we know we burn something, exothermic means I want it to happen. And when delta S is entropy, when is that more likely to happen? When things spread out. So when it's positive, right here, okay? So if I have delta H negative, delta S positive, then when is that going to tell me about how do I figure out if something is favorable? And the answer is we use a new equation called Gibbs free energy. So Gibbs free energy tells us how favorable something is based on the enthalpy and the entropy of something. But I write it out like this. So in your equation sheet, you have this term delta G, which is Gibbs free energy. The change in energy, change in delta G, is delta H, which is enthalpy, minus T delta S. And this is the absolute temperature in Kelvin. Okay, so if I change temperature, is that going to affect how fast something goes? Yeah. Like if I heat something up or cool something down, it's going to affect the scenario. It's going to affect the situation. So T has a pretty big role in something. So let's take a look and see what does this mean. If I have delta H, so when is anything going to always be favorable? So delta H, remember, is when that's negative. So what's it? Exothermic. And when delta S is spreading out and is positive, then what happens to delta G? Well, I have a negative number minus a temperature times a positive number. And remember, T is always positive because it's always in Kelvin. So if I delta H is negative minus a positive number, what will delta G always be? Well, if this is the case, then delta G is negative when it's always favorable. Okay. So if delta G is negative, if this is negative here, and this is positive here, then delta G is negative for a favorable scenario. Well, what if you have the opposite? If this is positive and this is negative, if I have an endothermic and entropy is decreasing, is that going to want to happen? And no, that's never going to happen. So if delta H is positive and delta S is negative, I have a positive number minus a negative, which is positive. That makes delta G positive. Okay, so for delta G, so let's just go through the scenarios. If delta G is negative, always spontaneous, always favorable. If delta G is positive, it's never going to happen. And if it's at 0, then we actually have equilibrium. And we'll do some calculations with that. So let's look at how this plays out. Well, if I have different scenarios, I have positives and negatives, what do we talk about? We talk about this one first. Negative delta H, positive delta S. What's always going to happen? Delta G is always going to be negative here, so we always have favorable. What's our opposite? If I have positive delta H and negative delta S, that's always going to be positive delta G. Never going to happen. What if we have a negative delta H, so it's exothermic, but delta S is negative, also negative. So this is negative, this is positive. Well, if T, this is where T comes in. So if T is small, let's say this term right here, it's not really going to make a difference, right? So if delta H is negative and if T is small, well then delta H takes over. So this is ruled by delta H. And that means, well, overall delta G is negative. Okay, so delta H, I want to say I wrote delta H here, but it just means delta H is kind of in charge here. So this is in charge. What if the reverses happen? Well, if I have delta H is negative, but this is a big delta T. So if this term now is big, well then this kind of, that kind of doesn't factor in. And if this is a minus a negative and it's really big, then all of a sudden what happens, G can end up being positive. Okay? So in different scenarios, you can have a flip in the sign of delta G because this one, delta S, is in charge. So delta S is in charge here, and that makes it positive. And if I did the other ones here, so let's say delta H is positive and T is small, well then what does that do to my two values? Well, delta H is in charge, right? So delta H is in charge, and that means delta G is positive. Or over here, the opposite occurs. Delta S is in charge. So if this is positive, but this is a big delta S, so this L delta S times T, then my delta S is in charge. That makes it negative, drives it down. It wants to spread out, and that makes it delta G negative. So we have some scenarios. We gotta think those through sometimes, and we'll do some practice with this in class.